All right, can you see that?
Yeah, perfect.
Excellent. All right, well, thanks, Rachel, for introducing me and also for organizing the symposium. And thanks to all of you for coming. I'm going to talk about a bunch of different projects with co-authors Ted Grosholtz, Brian Turner, Greg Ruiz, Carolyn Teepolt, and others. And as you can see, I study in the marine realm, but I think the conclusions are going to be relevant to many of you as well. And I'm really interested in whether we should manage at all. And I'm going to present some science about what considerations we've come to for determining if we should try to eradicate or otherwise control European green crabs, or I'm going to drop the European, and sometimes I'd like to call them five-spine shore crabs because you'll see they're not really green either. So these crabs can reach really high abundances, as you can see here, and they are voracious eaters of clams, competing with shorebirds and other crabs, et cetera. They eat other crabs when they're smaller, including juvenile Dungeness, et cetera. So they're a species of concern. They're a really successful global invader. With my advance isn't working, there we go. With climate change, their range can expand. It's already vast, and you can see here on the left larval development modeling. So we raise larvae at different temperatures and then use that with water temperatures to predict where they could live. You can see in the green where they are currently in their range, and the blue is what's suitable conditions for them, but they didn't live in 2007. Since then, they've actually expanded to some of these areas on the West Coast as well as the East Coast. This invasion started in the late 80s in San Francisco Bay, and they've spread quite rapidly since then. Interestingly, in the purple are areas that were at the time not deemed suitable for their larvae to develop. That's sort of a more fragile stage than their adults. And they do disperse on currents up the coast and down the coast, typically down the coast, but on El Nino years, they can spread northward too, and clearly have from San Francisco Bay quite a bit. So they had established fairly early in Oregon, but really low numbers, and the age cohorts pretty much would die off until the next El Nino. And here you can see that with warming, they were predicted to come in Oregon. Starting about 2 years ago, their numbers really started increasing in Oregon. And now, I was just out on the coast last weekend, I saw so many green crabs and really big ones too. So they're definitely here to stay. And you can see also with this 2 degrees of warming from 2007, it was predicted that they can get to even more of the Alaska coast. So huge amount of coastline yet to be exploited, including the current conditions and slightly warming conditions. On the right side is environmental niche modeling that we did with Maxent, and that similarly shows for both of these, there's no loss of range on the West Coast with warming, just expansion, and that they could get up. This predicts even farther up into Alaska. So concern, in addition to expansion of range that can happen with warming, I was interested in how much predators are going to react to changes in temperature, in water temperature. On the East Coast, and I'll just touch on this briefly, we found that blue crabs, Callinictes sapidus, restrict the range of green crabs, and both within estuaries and throughout their range. And on the West Coast, some nice work by Hunt and Yamada in 2004 looked at how these red rock crabs also can restrict them with red rock crabs, which are really marine crab, keeping green crabs in estuaries pretty much, where the water is fresher and red rock crabs can't thrive. So we had on this coast, unlike elsewhere in their ranges, they're really restricted to estuaries. Well, looking at predation by these different crabs and by green crabs themselves on smaller green crabs across temperatures, we can see that blue crabs do just fine at warmer temperatures, exert high predation levels on green crabs. Here's the mean proportion of green crabs eaten. But the red rock crabs peak with their predation at about 12 degrees, so still pretty cold water. And then after that, they actually don't exert any predation at all. At our higher temperatures, they all died. And so they definitely weren't creating a predation risk and biotic resistance to green crabs. So this is really important. Not only are the green crab ranges going to change with temperature, with warming waters, but because of direct effects, but indirectly due to the effect of temperature on red rock crabs. And that's just thermal changes from global climate change. There's also going to be changes in dissolved oxygen and upwelling, in salinity due to rain coming into our estuaries, et cetera, all of which are going to reduce, theoretically, predation by red rock crabs. And in fact, recently, there's been a couple sightings of green crabs off the coast on this coast, which again is likely due to red rock crabs not providing the biotic resistance that they had before. This is worrisome to me. Luckily, red rock crabs aren't the only predator on this coast. Sea otters and river otters both eat green crabs. Here in Elkhorn Slough, you can see an otter just chowing down on this green crab. And in fact, green crab numbers have plummeted in the slough since sea otters have really started using that as a grazing ground. Leopard sharks also eat small crabs and might be an important predator too. They don't get further north though. So I would put this in the RAD framework into direct, I believe, where if we can help predators thrive, then that might help us in our management of problematic invasive species. Because we can't just rely on predators, though, we tried some removal experiments. And this particular one, I'm going to talk about two. First one here in Seadrift Lagoon, which is off Bolinas Lagoon, just north of San Francisco Bay in central coastal California. Later, I'll talk about one in Bodega Bay, which is one of our reference bays, along with these others for this current part of the work. And you can see that we removed green crabs from Seadrift Lagoon, this sort of man-made lagoon here that's connected to the greater Bolinas by a tide gate. This becomes relevant later. And you can see in 2009, we got about 25 crabs per trap. And then with time, we brought them down till in 2013, we were just getting 1 or 2. This was a great success thus far. And we wanted to remove them just to see what happened, to make sure you can as a test before we expanded this effort elsewhere, and to look at how populations of their prey rebounded once we removed them. And here you can see for estimated population size in 2009, there were about 125,000 green crabs in this little lagoon. And by 2012, there were just a couple thousand. So we came back in 2014 to mop up the last of them and check on prey rebound. And instead, we were horrified, quite literally, by what we found. And that is really high catches in our traps. And you can see here the estimated population size from mark recapture. We are wanting them to see if they've been captured before. And you can see that we had over 3 times the original population size, over 30 times the amount from the year before. We then started removing again, though, so it's a little lower in 2015 again. So we wanted to know if this is overcompensation. Overcompensation can occur, it was first modeled for fishery species, when you remove the target species, in this case our invasive species, to remove them for harvest or because they're an invader with impacts. And then overcompensation is when that population not only rebounds, but becomes higher than the original population. And it sure looks that way, but we wanted to experimentally examine this. We had the reference base. So the first question is, well, was that high recruitment that we saw in Seadrift also true for those other bays? Look at 2014. And you can see zero recruitment there, zero recruitment into Mollusk Bay, that just wasn't the case. Really, this was a Seadrift phenomenon. So that does make it seem like it's overcompensation. For overcompensation, you'd expect a whole bunch of juveniles. And indeed, the blue here and the green are all pre-reproductive, or at that time we expected pre-reproductive. Crabs are mostly juveniles, shown here. The carnation color here is their over 15 millimeter carapace with adults. And one interesting thing is that this particular year, for the first time, we saw crabs, really tiny ones that we never would have seen with eggs before, just these small sort of 35, 33 millimeter carapace with crabs with eggs. So they were reproducing earlier as well. We did not see the same recruitment again in nearby Bodega Harbor. So why did this happen? And should we be worried for other species of this happening? Certainly there have been instances in lakes and some rivers with fish showing the same overcompensation in response to an eradication attempt. And what those show, and what we found here in experiments, is that adults either eat or compete with, in our case, both the juveniles. And here we can see the likelihood that juveniles are eaten by adult green crabs, and that it was most likely to happen when the adults were much larger than the juveniles. So you can see up here that this is the data. They were eaten across all size ranges, but especially when they were when the juveniles were much smaller than adults. And they were less likely to be eaten when they're about the same size. In addition, there's competition. It's the number of clams consumed in over a day by 4 juvenile crabs. I told you they can eat a lot. And if they're with an adult, even though the adult in this case had mittens on, so couldn't eat them, their predation really decreased on clams compared to if there's no an adult in the container too. So for these species where there's suppression of juveniles by adults, they're certainly susceptible to compensatory growth, that they rebound from eradication, or overcompensation, that they more than rebound. We also had molecular evidence that that there's local recruitment in our removal lagoon, Seadrift. All of these crabs in Seadrift were genetically distinct from the ones on the outer coast. In pink is British Columbia, and the other populations in Oregon, Washington, and California are sort of lumped together. This paper just came out this week, and we also found that there's, I'll keep it short, I know I'm behind in time. It shares the genetic mechanism by which you can have rapid adaptation despite having a bottlenecked population. All right, so as I said, we also did removals elsewhere, and this, I think I skipped a slide, I did. And this includes Bodega Bay. And this is important in our conclusions in that we did get overcompensation in Seadrift, but we didn't in Bodega Bay. And you can see that here. This is the proportion of newly recruited green crabs, and in Bodega Bay in red compared to other bays in these other lines. And you can see that Bodega Bay, once we started removal, didn't have much higher proportion of juveniles. So we don't get that same recruitment pulse that we found eventually in Seadrift. This paper was published in 2009, but we continued still to monitor them, and they still haven't had that big recruitment pulse. So we didn't get the overcompensation. Why is that? This variation within a species. One of the reasons is likely that Bodega Harbor is a really open population. Juveniles recruit in as larvae from other populations, whereas that's less the case in Seadrift, you'll remember I said it's connected with a tide gate. So that's often closed and only sometimes open. In this literature review paper by my lab alumni, Dr. Brian Turner, you can see that if a population is closed, like a lake or a closed lagoon, most likely there's, in the papers he reviewed, which are mostly on fish eradications, there was no evidence of compensation rebounding to the regular or initial population size or overcompensation beyond it, although there are a couple examples of that. In open populations here, in the middle bars, we can see that it's much more likely that there's compensation. And in variable populations are only examples of overcompensation. That's like if there's a lake that's sometimes connected with inflow and outflow with rivers, or like in Seadrift Lagoon, tide gates sometimes open, there's more than half likely to have compensation or overcompensation. So the connectivity of the site is actually really important. Thermally, it might be important too. Seadrift being enclosed and shallow is warmer. So back to our temperature connection. A third difference also is for our removal in Bodega Harbor, we just weren't as successful at first. We did bring numbers down quite a bit from before in the green to after in the white bars, really bring down the number in traps, and also with mark recapture population estimates compared to the reference bays. But we didn't bring it down as dramatically as with Seadrift. And so maybe just always having those remaining adults behind really was helpful. So this is still, I think, in the RAD framework under resist. It's just not going all the way to full removal and eradication, but bringing us down so there's still those functioning adults to suppress the juveniles, but allowing, ideally, the prey to respond. And we did measure that, and you can see that here we are in Bodega Harbor, our removal bay, that indeed these shore crabs, which are prey of the green crabs, and you can see here, green crab eating one, they did rebound right away in the first year, and that, I'm not showing that here, but that persisted over time. They happened to go up in reference bays too, but the statistics show that they went up more in our removal bay proportionally than in these reference bays. And in addition, they were larger in size even within a year after, so they quickly rebounded and grew in size, which allows them to further increase their population size as larger females produce more eggs. We can directly pin this to green crabs for a number of reasons here. This one here, we tethered, you can see this little tied up shore crab here. We tethered these shore crabs and put them out across different densities of green crabs. And you can see that more shore crabs are consumed with more green crabs. So the native population rebounded even with this partial removal. All right, so what conclusions are there for management? One, obviously prevention. Vector management is key here. Second, I'd really like to push modeling species that can arrive just normally and perhaps thrive with climate change. One thing I didn't talk about or only mentioned is with climate change also, it's habitat changes as well as range expansions. And that really comes into play also if we look at consumers and how they're also affected by climate change. So simple models with niche models, but also perhaps more complicated ones looking at climate effects on major consumers. Of course, local and regional management plans, especially with these species that have connectivity, pretty openly connected systems. Regional plans are really key because otherwise there's just always this recruitment from elsewhere. Funds sitting around to eradicate new incursions, because as you can see from this work, it's really key not to let your population grow huge. And we know that takes rapid response, and also that that's much cheaper overall to get the same good outcomes when you can even get good outcomes. And monitoring and outreach, it's really important to have many eyes on the ground. For control, manage early, encourage local predators to maybe get to the direct we know it's happening. Let's direct how it happens so that we can get that biotic resistance here, manage to prevent population boom, and research of climate change effects. And then if the problematic populations are large, to really assess this potential for overcompensation so that you don't remove them and end up with even more. Do they have a high reproductive rate? Are adults suppressing juveniles through competition or cannibalism? Is the system open or variable? And then also, if you are going to proceed, maybe remove reproductive females first, leaving in big males, in our case, as they were the ones that are most consuming and competing with the smaller green crabs. And another thing that would have been effective is just reducing them all at once, getting them before they really established and had limited their own food source and are really reducing each other, eating each other instead. Or maybe just removing them just enough to minimize their impact and unintended growth. So those are some of my conclusions. I'm still really mentally in this resist part of the RAD framework, but I'm interested in hearing these other talks, and thanks for both Toms for their talks today in exploring those other options as well. I'd like to thank the funders, people who shared data, many co-authors who wasn't able to put on the first page, and all the other people who helped with the work. And I'd also like to acknowledge that where we did the lab work and where I am in work is unceded territory of the Multnomah and other tribes of the Columbia River, and the field work, of course, includes unceded lands of many other peoples. And thank you all for listening. I'll welcome your questions when we get there.